We have mapped light that left its source before Earth existed. We have weighed galaxies we will never visit, timed the heartbeat of atoms, traced the birth of matter itself back to a single blistering fraction of a second. In many ways, we understand more about existence than any generation of humans ever has. And yet, the honest answer is this: we have barely started reading. Picture the universe as a book. Not a book you skim on a lazy afternoon, but one you are reading with a flashlight, in the dark, page by page, only just now realizing something is deeply wrong with the copy in your hands. Some pages are stuck together, refusing to separate. Others have been torn out entirely, leaving jagged edges where the story should continue. A few pages are written in a script no one has ever learned to read. You are holding that book right now, and once you notice the damage, you cannot unsee it. Why does the sky point in one direction, as if something outside the book left a thumbprint on the page? Is there a scar stretched across our sky, a bruise left behind by another universe brushing up against our own? Why did space expand too fast, too early, before it had any right to? Why do galaxies that are far too mature, too structured, too complete, exist in an era when they should still be infants? And why do walls of galaxies stretch across distances so vast that the universe may not have had enough time to build them? 5 missing pages. 5 torn edges in the story of everything. And by the end of this, you will understand exactly why scientists still cannot explain any of them. If you have ever scrolled past one of those famous mottled images from NASA, the ones that look like a spilled bag of orange and blue confetti, and thought there was something almost too orderly about the pattern, you were not imagining it. That image is the oldest light in existence, the afterglow of a universe still cooling from its first violent moment. And for decades, scientists have been staring at it the way you might stare at a photograph that seems perfectly ordinary until you notice a face hidden in the wallpaper. That light is called the cosmic microwave background, and it is, in the simplest possible terms, an echo. Roughly 380,000 years after the beginning, the universe cooled just enough for light to finally break free and travel without being trapped and scattered by a dense fog of charged particles. That light has been traveling ever since, stretching as space itself stretched, until it arrived at our telescopes as faint microwaves instead of blinding radiance. When we map it across the entire sky, we are not looking at stars or galaxies. We are looking at a snapshot of everything, taken almost at the very start of the story. And here is the part that should feel comforting: that snapshot is almost perfectly smooth, almost featureless. The temperature varies by only a few parts in 100,000 from one patch of sky to the next, which is exactly what a well-behaved, evenly expanding universe should look like. Cosmologists spent years hunting for the tiny ripples in that smoothness, because those ripples are the seeds that would eventually grow into galaxies, into clusters, into everything we now call home. Find the ripples, understand the ripples, and you understand how a bland fog of hot particles turned into a universe capable of producing stars, planets, and someone capable of asking questions about it. They found the ripples. That part of the page reads exactly as expected. But then someone looked closer at the largest ripples of all, the broadest, faintest patterns stretched across the entire sky, and noticed something that should not have been there. When you break the temperature map down into its biggest, simplest components, the very largest structures in that ancient light are unusually weak, fainter than a random, structureless universe should produce. That alone is strange enough. But the stranger detail is the direction those weak, oversized patterns point. There is a preferred axis running through the data, a line you could draw across the sky, and the largest features in the oldest light in existence line up along it far more than chance should allow. Scientists eventually gave this alignment a name that was only half a joke: the axis of evil. Not because anything sinister is happening in a literal sense, but because if a universe is supposed to have no preferred direction, no favorite axis, no built-in arrow pointing anywhere in particular, then finding one feels like catching the story breaking its own rules. Here is where the page gets torn in a specific and uncomfortable way. That axis does not point towards some random patch of empty sky. It roughly lines up with the plane of our own solar system, the flat disk along which Earth and the other planets orbit the Sun. Picture holding up that book again, and instead of a torn page, imagine a crease running through it that just happens to line up perfectly with the edge of the desk you are reading it on. The oldest light in the universe, a signal that supposedly has nothing to do with our tiny corner of space, appears to be nodding toward our own solar system's orientation. That single detail is what turned a curious statistical anomaly into one of the most argued over puzzles in modern cosmology, because it forces a choice between three explanations, and every one of them comes with a problem. The first explanation is the one every cosmologist secretly hopes is true, because it would mean nothing is actually broken. In this version, the alignment is a coincidence, a fluke produced by the fact that we only have one universe to observe and one sky to measure it from. Statistically, when you are working with a single sample and a limited number of large-scale features, unlikely-looking alignments will occasionally appear by pure chance, the same way a shuffled deck of cards will occasionally produce a pattern that looks meaningful even though it isn't. Run the numbers enough times, the argument goes, and eventually something in the sky will happen to point somewhere. Under this explanation, the standard model of cosmology stays intact. The smooth, direction-less universe we expected is still correct underneath, and the axis is simply an unlucky roll of cosmic dice that happened to land near our own backyard. The problem is that the odds being quoted for pure coincidence are not comfortable ones. Several independent analyses, using different satellites and different methods, keep finding the same unlikely alignment rather than it washing out as more data comes in, which is exactly the opposite of what you would expect from a fluke. The second explanation is less exotic and, for a while, was the leading suspect: contamination. The signal we are measuring did not travel to us through empty space alone. It had to pass through our own galaxy, through clouds of dust and gas, through the glow of the Milky Way itself, and through the solar system's own faint foreground emissions, before it ever reached a detector. If some of that local material was not perfectly subtracted out of the data, it could leave a residual smear behind, a smear that would naturally be oriented along the plane of our solar system, because that is the plane most of the contaminating material sits in. Under this explanation, there is no cosmic mystery at all. There is only an uncleaned window, a bit of fog on the lens that happens to be shaped like our own orbital disk, and once instruments and analysis techniques improve enough to wipe that fog away completely, the axis should simply vanish, revealing the plain, unremarkable sky underneath. For years, this was the safest, most boring, most reassuring answer. Except later missions built specifically to be more sensitive and to better separate foreground contamination from the true ancient signal did not make the alignment disappear. It weakens slightly in some analyses, strengthened in others, and stubbornly refused to be explained away completely, the way a smudge should behave once you finally clean the glass properly. Every improvement in equipment was supposed to be the moment this problem quietly resolved itself. It has not. Which leaves the third explanation, the one that keeps cosmologists awake, because it does not blame our instruments or our luck. It blames the earliest moment of the universe itself. In the standard picture, the universe underwent an incredibly brief, incredibly violent burst of expansion at the very beginning, a period that smoothed out irregularities and is supposed to have erased any memory of direction, any preferred axis, any built-in arrow. That process is assumed to have been perfectly even in every direction, which is precisely why a directionless, isotropic sky is the expected outcome. But if that early expansion was not perfectly even, if something about the initial conditions, some structure, some field, some asymmetry present before that expansion even began, nudged the universe to stretch slightly more in one direction than another, then a faint preferred axis would be exactly the kind of fingerprint left behind. Under this explanation, we are not looking at a coincidence, and we are not looking at dust on the lens. We are looking at a scar from the very first instant of existence, a moment so early that almost nothing else survived to tell us about it, except this one stubborn, misaligned pattern stretched across the whole sky. If that third explanation turns out to be correct, the implications reach far beyond one strange alignment. It would mean the founding assumption behind nearly every calculation in modern cosmology, the assumption that the universe looks the same in every direction, is not quite true. And once one assumption like that cracks, every measurement built on top of it, the age of the universe, the rate of its expansion, the models describing how galaxies formed, all of it would need to be revisited with a universe that has, however faintly, a favorite direction. No satellite mission has settled which of these three explanations is correct. Newer surveys have narrowed the odds against pure coincidence, weakened but not eliminated the contamination argument, and left the deepest explanation, an asymmetry baked into the very beginning of everything, sitting there unresolved, neither proven nor ruled out. The axis is still measured. It still points, faintly but persistently, toward the plane we happen to be sitting in. And the honest answer, the one that will not change no matter how many times you refresh the latest paper on the subject, is that nobody currently knows for certain why the oldest light in the universe seems to be looking directly at us. That is the first torn page, and it will not be the last strange thing this sky has been hiding. That misaligned axis, stubborn and unresolved, is not the only place where this ancient sky refuses to behave the way a smooth, uniform universe should. There is a second oddity hiding in the same map, one that barely gets discussed outside physics departments, mostly because almost nobody knows how to explain it without sounding like they are describing science fiction. And that is precisely the problem. If the explanation that keeps surviving every attempt to rule it out turns out to be correct, it would mean our universe brushed up against something else before it had even finished being born. Somewhere in that mottled map of the oldest light in existence, there is a patch of sky that is colder than it has any right to be. Not colder by a small, forgettable margin. Colder in a way that stands out from everything surrounding it, a dip in temperature spanning a region of sky large enough that if you held up your hand at arm's length, it would barely cover it. Astronomers call it, without much poetry, the cold spot. And ever since it was first noticed, the question hovering over it has been disarmingly simple. What if the coldest spot in the sky isn't cold by accident? To understand why that question is so unsettling, you have to remember what the cosmic microwave background actually is. It is the afterglow of the early universe, a faint bath of radiation left over from the moment light first broke free to travel unobstructed across nearly the entire sky. That afterglow varies only slightly from one patch to the next, tiny ripples representing tiny differences in density, the seeds that would eventually grow into galaxies. Almost everywhere you look, those variations behave exactly as expected, modest, statistically ordinary, well within the range that a smooth, evenly seeded universe should produce. The cold spot breaks that pattern. It is far larger and far colder than the standard model comfortably allows, sitting near the outer edge of what could plausibly happen by chance. That alone would be enough to earn it a footnote in a textbook. What turned it into something closer to an obsession is that every attempt to explain it away with an ordinary, boring cause has run into trouble. The first suspect, and by far the most sensible one, was a foreground problem, the same kind of issue that muddied the axis alignment. Before the ancient light from the early universe reaches a telescope, it has to pass through everything sitting between us and it, gas, dust, and crucially, the vast structure of galaxies and voids scattered across billions of light years. If a giant, unusually empty region of space, a supervoid, happened to sit directly along our line of sight to that patch of sky, it could genuinely cool the light passing through it. As ancient light travels through a region with less matter than average, it should lose a small amount of energy on the way, a well-understood effect where light climbing out of a shallower gravitational dip than expected comes out slightly less energetic, and therefore slightly colder by the time it reaches us. This explanation had real appeal because astronomers actually found a candidate. A survey of galaxies in roughly the same direction as the cold spot revealed an enormous supervoid, a region of space stretching for hundreds of millions of light years with dramatically fewer galaxies than the surrounding cosmic average. For a while, this felt like the tidy resolution everyone wanted, no exotic physics required. Just an unusually large, empty patch of space, doing exactly what empty patches of space should do to light passing through them. Except when researchers actually calculated how much cooling a void of that size and depth should realistically produce, the number came up short. Not by a small rounding error, but by a significant margin. The known physics of light traveling through large-scale cosmic structure could account for only a fraction of the cold spot's actual depth. The supervoid was real, its cooling effect was real, but it was nowhere near enough, on its own, to explain the anomaly it was supposed to solve. That left researchers with an uncomfortable choice. Either there was some additional physical effect boosting the cooling far beyond what standard calculations predicted, some subtlety in how light interacts with enormous underdense regions that current models were failing to capture, or the supervoid was a real but coincidental structure that happened to sit in the same general direction as a cold spot with an entirely different origin. Either way, the tidy explanation was no longer tidy. The page that seemed like it had finally been read correctly turned out to still be glued shut in places. And so a second, far stranger explanation returned to the table, one that had originally been proposed almost as a thought experiment and was suddenly being taken seriously again. What if the cold spot is not a void at all, not a trick of foreground structure, but a direct imprint from the single most extreme event in the universe's entire history, the moment of inflation itself. To understand this idea, you have to picture the earliest sliver of time in the universe's existence, a period so brief it is measured in fractions of a second, during which space itself is thought to have expanded at a staggeringly accelerated rate, stretching a region smaller than an atom into something vastly larger in an instant. This process, known as inflation, is the leading explanation for why the universe today looks as smooth and evenly spread out as it does. But many versions of inflationary theory carry a strange and largely unavoidable side effect. If inflation happened once, in one small patch of some larger pre-existing space, there is no obvious reason it should have happened only once, and only there. Under this framework, called eternal inflation, our own universe would be just one bubble among an enormous, possibly infinite number of other bubbles, each one a region where inflation ended and a universe like ours began, all of them expanding within some larger, still inflating space that never stops stretching. Most of the time, in most versions of this idea, these bubble universes would be so far apart and separated by space still expanding faster than light could ever cross, that they would never interact, never touch, never leave any trace on one another at all. But not always. In some of the mathematics describing this scenario, two bubbles can, under the right rare conditions, collide before they drift too far apart, back when both were still young and close enough for interaction to actually matter. A collision like that would not look like two solid objects crashing together. It would look like a disturbance in the underlying field driving inflation itself, a bruise in the fabric of whatever came before our own universe's specific burst of expansion. And when the light from our universe's earliest moment finally formed and began traveling toward us billions of years later, that ancient bruise, if it existed, would still be stamped into it, showing up today as a region of the sky that is unusually cold, unusually large, and unlike anything a smooth, single-origin universe should produce on its own. Sit with that for a moment. A cold patch of sky, roughly the size you could block out with an open hand held at arm's length, may be the closest thing modern cosmology has to physical evidence that our universe once touched another one, before either had finished forming. This is not a fringe idea whispered only in speculative corners of physics. Researchers have run detailed simulations modeling exactly what a bubble collision imprint should look like statistically, what its edges should resemble, how sharply its temperature should drop compared to a natural void, and compared those predictions directly against the observed cold spot. The comparisons have not produced a clean, dramatic confirmation. But they have not ruled the idea out either. The cold spot's shape, its unusual sharpness at the edges compared to what a slowly forming void would typically produce, its stubborn refusal to be fully explained by the supervoid discovered along its line of sight, all of it keeps this far stranger explanation alive on the list of serious possibilities, rather than letting it quietly fade into obscurity the way most exotic proposals eventually do. Of course, the supervoid explanation has not been abandoned either, and newer, more detailed surveys of the galaxies in that direction continue to refine exactly how much matter is missing, and exactly how much cooling that missing matter can plausibly produce. Some analyses have found the void slightly less extreme than first measured, which only widens the gap between what ordinary physics predicts and what the cold spot actually shows. Other analyses have pushed back, arguing that once every subtlety of light traveling through a large, irregularly shaped underdense region is accounted for, including effects beyond the simplest calculations, the gap narrows considerably, perhaps enough to close it entirely. The debate has not settled. Different teams, using different surveys, different statistical methods, and different assumptions about how completely we understand large-scale cosmic structure, continue to arrive at meaningfully different answers. What makes this puzzle different from an ordinary unresolved detail is the sheer weight of what sits on either side of the answer. If the mundane explanation eventually wins, if some refined understanding of supervoids and light propagation fully accounts for the missing cooling, then the cold spot becomes a fascinating but ultimately explainable feature. A large empty region of space doing something slightly more dramatic than first calculated. Nothing more. Cosmology stays intact. The multiverse remains an untestable mathematical possibility rather than something with a genuine fingerprint on the sky. But if the mundane explanation keeps failing, if every refinement to the supervoid calculation continues to fall short of the observed depth, then the far stranger explanation is left standing not because anyone particularly wanted it to be true, but because nothing else fits the data as well. And that would mean scientists are not simply debating an unusual patch in an old photograph. They would be looking directly at a scar, a bruise carried in the oldest light we can observe, left behind by contact with something outside the only universe we have ever been able to study. No survey has delivered a final verdict. The supervoid is still there, still measured, still slightly too weak to fully explain what it sits in front of. The bubble collision models are still being refined, still compared pixel by pixel against the sky's actual data, still neither confirmed nor discarded. The honest, current state of the science is this. Nobody knows for certain whether the coldest region of the sky is an ordinary cosmic accident or the only piece of direct observational evidence, however faint and contested, that our universe was never truly alone at the very beginning. That is the second glued-together page in this book we are reading. One shows a universe that appears to remember a direction it should never have had. The other may show a universe that remembers touching something else entirely. And if you think those two anomalies are strange enough on their own, the next page in this story asks a question that cuts even deeper. One that does not just challenge what the universe looks like, but how fast it grew up in the first place. A universe with a favorite direction. A cold patch that might remember touching something else. Two torn pages, both still unread in full. But the next one might be the strangest of all. Not because it involves some exotic collision billions of years in the past, but because it involves a number we assumed we already knew. How fast the universe is expanding right now, today, in the only era we will ever actually live in. We have built our entire model of the universe assuming that number would come out the same no matter how you measured it. It does not. Start with the oldest method, the one that treats the universe like a crime scene reconstructed from its earliest surviving evidence. That ancient afterglow of light, the same faint bath of radiation carrying the misaligned axis and the mysterious cold patch, contains far more information than just temperature ripples. Buried in the statistical patterns of those ripples is a kind of fingerprint left by the physics of the early universe, how much ordinary matter existed, how much dark matter, how the whole mixture behaved as it cooled. Feed all of that into the equations that describe how a universe like ours should expand over time Run the model forward billions of years to today, and it spits out a very specific prediction for how far space should currently be stretching apart. That number comes with remarkably small uncertainty because it is built from an enormous, exquisitely detailed map of nearly the entire observable sky. Now take a completely different approach, one that ignores the ancient afterglow entirely and instead measures the universe the way you would measure distance in your own neighborhood, by looking at things you can actually see and calculating how far away they are and how fast they're receding. Astronomers use certain stars that pulse with a brightness so mathematically predictable that measuring their pulse rate tells you their true luminosity, and comparing that true luminosity to how dim they appear from here tells you, with real precision, exactly how far away they are. Chain enough of these reliable cosmic distance markers together, out through neighboring galaxies and beyond. Compare those distances to how quickly each galaxy is rushing away from us, and you get a second, independent measurement of the same expansion rate, built entirely from the nearby present-day universe rather than its infancy. Two completely different methods, two independent lines of evidence, one anchored in the earliest possible moment we can observe, one anchored in the universe as it exists right now. And for a long time, the expectation was simple. If our model of the universe is correct, both methods should converge on the same answer, because they are measuring the exact same quantity, just approached from opposite ends of cosmic history. They do not converge. The early universe method consistently predicts a slower expansion rate than the late universe method actually measures. And for years, the polite assumption was that this was simply measurement error, the kind of small mismatch that shows up constantly in science before someone finds the overlooked calibration issue or the subtle bias in one of the techniques. Every field has disagreements like this. Most of them quietly resolve themselves as instruments improve and datasets grow. This one didn't resolve. It got worse. As telescopes improved, as the pulsing star distance ladder was checked and rechecked using multiple independent calibration methods, as the ancient light method was refined with newer, more sensitive space missions. The gap between the two answers did not shrink toward agreement the way a simple measurement error should. It held steady. Then it sharpened. Independent teams, using different instruments, different galaxies, different statistical techniques, kept landing on the same two incompatible numbers over and over, with the uncertainty on each measurement shrinking every year, while the gap between them refused to close. In science, when two independent, high-precision measurements of the same quantity disagree, and that disagreement survives every attempt to explain it away through better data or better technique, you eventually run out of room to call it a rounding error. That's roughly where this stands today. A few years ago, this discrepancy could still be waved off as noise, a curiosity worth watching rather than worrying about. But here's where it stops being a rounding error and starts being a 5-alarm fire for cosmology. The statistical confidence behind this mismatch has now climbed to a level where, in almost any other area of physics, it would already be treated as a confirmed discovery rather than an open question. This is not two teams squinting at fuzzy data and arguing over interpretation. This is dozens of independent measurements using fundamentally different techniques, converging on two numbers that simply refuse to be the same one, which means one of two things has to be true, and neither of them is comfortable. Either there is still some undiscovered, deeply hidden flaw in how we calibrate one or both of these measurement chains, Some systematic error clever enough to survive a decade of increasingly aggressive scrutiny from rival teams actively trying to find it. Or our model of how the universe expands, the same model that has successfully predicted an enormous range of other observations, is quietly missing something fundamental about how the cosmos actually behaves between its infancy and now. If it's the second option, the possible culprits are not small tweaks, they are missing ingredients. One candidate points at dark energy itself, the mysterious force, like property of empty space, that is causing the universe's expansion to accelerate. The standard model treats it as a constant, an unchanging pressure baked into the fabric of space that behaves identically at every point in cosmic history. But what if it isn't constant? What if dark energy's strength has shifted over the roughly 13.8 billion years of cosmic history? Weaker in the deep past and stronger, or differently shaped as the universe aged? A dark energy that evolves over time, rather than staying frozen at a single unchanging value, could plausibly stretch the early universe prediction and the late universe measurement apart in exactly the way we're now seeing, reconciling both without throwing out either measurement as flawed. A second candidate points somewhere even less visible: neutrinos, the almost massless, barely interacting particles that pour out of nuclear reactions by the trillions and pass through ordinary matter, and through you, constantly, without leaving a trace. The standard model of cosmology makes assumptions about how many types of neutrinos exist and how much mass they carry, assumptions baked directly into the equations used to interpret that ancient afterglow of light. If those assumptions are even slightly wrong, if there's an extra flavor of neutrino we haven't accounted for, or if their collective mass is different than assumed, the early universe prediction for today's expansion rate would shift, potentially closing the gap with the late universe measurement without requiring dark energy to behave any differently at all. A third possibility is the most unsettling, precisely because it doesn't offer a single new ingredient to add to the recipe. It suggests the entire recipe, the standard framework describing how the universe is built and how it evolves, the same framework that has quietly succeeded at predicting an enormous range of independent observations for decades. Might be structurally incomplete in some way nobody has correctly identified yet. Not wrong in the sense of needing to be discarded entirely, but wrong the way a map can be correct about every road you've personally driven while still missing an entire district you've never visited. Under this possibility, the discrepancy isn't a clue pointing at one missing particle or one misbehaving force. It's a symptom of some deeper structural gap in how we currently describe the universe's growth from infancy to now. A gap serious enough that patching it might require rethinking assumptions considered settled since long before this discrepancy was ever taken seriously. None of these explanations has won. Dedicated survey missions have been built specifically to pin down the late universe measurement even further, using entirely new categories of cosmic distance markers alongside the pulsing stars, in the hope of proving the discrepancy is a calibration artifact after all. So far, those newer methods have mostly confirmed the higher expansion rate rather than undermining it, which is precisely the opposite of what you'd expect if the whole thing were a subtle measurement flaw waiting to be caught. Meanwhile, the ancient light measurement has been checked against entirely independent traces of the early universe, large-scale patterns in how galaxies cluster together across billions of light years, and those checks have largely reinforced the original early universe number rather than shifting it toward agreement. Two independent authors, each one working from solid, carefully checked evidence, each one confident in their own number, and neither one backing down. That is what makes this particular unread page feel different from an ordinary scientific disagreement. It isn't that nobody has checked the math. It's that everybody has checked the math, repeatedly, aggressively, from every conceivable angle, and the disagreement keeps surviving the checking. Consider what's actually at stake underneath all of this. The rate at which the universe is expanding today isn't just an isolated statistic. It threads through calculations for the age of the universe, the distances to the farthest galaxies we can observe, the timeline of when the first stars ignited, and the eventual fate of everything. Whether space keeps stretching apart forever, accelerating without end, or eventually reverses course. A discrepancy this small in raw numbers, roughly a 10% disagreement between the two measured values, sounds almost trivial stated plainly. But because that number feeds directly into nearly every other calculation cosmologists rely on, a persistent, unexplained gap here isn't a minor footnote, it's a crack running underneath the entire foundation, and nobody yet knows whether it's shallow enough to patch or deep enough to require rebuilding parts of the structure above it. What makes this especially maddening for anyone trying to follow along is that there isn't a villain to point at, no single bad measurement, no obviously flawed assumption sitting there waiting to be corrected. Every serious contender methodology has been stress-tested by rival groups actively hoping to find the other side's mistake. Because being the team that resolves this would represent one of the most significant results in modern cosmology. And so far, nobody has found it. Every year that passes without a resolution makes the boring explanations, sloppy calibration, and overlooked systematic error look less and less plausible, and makes the uncomfortable explanations, an incomplete model of the universe itself, look more and more like the only option left standing. Some cosmologists have proposed elaborate compromises, models that let dark energy shift character partway through cosmic history, models that add extra particle species to the early universe's recipe, models that tweak the balance of matter and radiation in ways subtle enough to avoid breaking every other successful prediction the standard framework has made. Each proposal manages to close the gap on paper. Each one, so far, has failed to satisfy every other piece of observational evidence simultaneously, solving the expansion rate discrepancy while creating small new tensions elsewhere, like tugging a blanket to cover one cold corner of the bed only to expose another. Which leaves this page of the universe's story sitting open, half-written, describing two numbers that were supposed to be the same measurement told from two different moments in cosmic history, and are instead behaving as though two separate authors wrote two separate endings without ever comparing notes. Maybe the resolution turns out to be quiet and technical, a subtle calibration correction discovered a few years from now that finally brings both sides into agreement. Or maybe the resolution turns out to be enormous, a genuinely missing ingredient in how the universe expands, one that forces a rewrite of the standard model's most basic assumptions. Nobody currently knows which. What is certain is this: the rate at which your own universe is expanding today, right now while you are reading this, is a number scientists cannot pin down with full agreement, and the gap between the two competing answers has only grown more serious the harder anyone has looked. 3 torn pages so far. A universe with a direction it shouldn't have. A cold patch that might remember something that happened before our universe finished forming. And now, a present-day universe that seems to be growing at two different speeds, depending on which end of history you measure it from. If you think that's already strange enough, the next page asks a question that shouldn't even be possible under the rules we thought we understood. What happens when telescopes start finding fully grown structures in an era of the universe still supposed to be in its infancy? A universe with a scar it shouldn't have. A cold patch that might remember another universe touching ours. Two competing speeds for the same expanding cosmos, refusing to agree. 3 pages torn or glued shut, and every one of them still open for debate. But the next page in this story does something stranger than all of them combined. It describes events that, according to the book's own timeline, have not happened yet. Here is the question at the center of it. How do you build a fully grown galaxy in the time it takes a baby to become a toddler? For decades, the story of how galaxies form was considered one of the more settled chapters in cosmology, not because every detail was known, but because the broad outline made sense and matched everything we could observe. In the beginning, matter is smeared out almost perfectly evenly across space, with only the faintest ripples of extra density here and there. Under gravity's patient pull, those tiny ripples slowly grow. Regions with slightly more matter attract slightly more matter, which attracts more still, in a process that takes real time to build any real bulk. First, small clumps of gas gather. Those clumps merge with other small clumps. Slowly, over hundreds of millions of years, those growing structures pull in enough material to trigger the birth of the first stars, then the first small, chaotic proto-galaxies, then, only after repeated mergers spanning enormous stretches of cosmic time, something resembling the large, structured, orderly galaxies we see filling the sky today, like our own. The key word in that entire process is time. Building a massive galaxy is not supposed to be fast. It requires generation after generation of smaller structures colliding and combining, a patient architectural project spanning the majority of cosmic history. Under the standard model, you should not expect to find large, mature, well-organized galaxies until the universe has had a few billion years to actually build them. Then, a telescope designed specifically to look further back in time than anything before it turned its mirror towards some of the faintest, most distant patches of sky and started finding galaxies that should not exist yet. To understand why this instrument changed everything, you need to understand what looking far away actually means in this context. Light travels at a fixed speed, which means the farther away something is, the longer its light has taken to reach us. Which means looking at extremely distant objects is the same as looking directly into the past. A galaxy whose light has been traveling for 13 billion years is not a 13 billion-year-old relic sitting somewhere out there today. It is a snapshot of what that region of space looked like when the universe itself was only a few 100 million years old, extraordinarily young by cosmic standards. This new telescope was built with the specific goal of catching that ancient, extremely faint, heavily stretched light, going further back toward the beginning than any instrument before it. And when it did, the results didn't just add a few more data points to the timeline of early galaxy formation. They broke it. Astronomers began identifying galaxy candidates from an era less than 500 million years after the beginning of everything. A period so early, it represents roughly the first 3% of the universe's entire history. In cosmic terms, that is barely a heartbeat, an infancy so extreme that under the standard model, only small, disorganized clumps of gas and young stars should exist, not fully formed structures. Yet several of these candidates appeared to be startlingly massive, some estimated to contain roughly as much stellar mass as galaxies that took the Milky Way billions of years longer to assemble. Worse, for the standard model at least, some of them appeared to already show structure, hints of an organized shape, rather than the chaotic, clumpy mess you would expect from a galaxy still in its earliest, most disorganized phase of construction. This isn't settled history you're hearing secondhand, safely filtered through decades of confirmed consensus. This is happening in real time, in active argument, as researchers pore over the same handful of extraordinary candidates, trying to determine whether they are exactly what they appear to be. The first and most important question every serious astronomer asks about a result this surprising is simple. Are we measuring this correctly? Determining a galaxy's mass and age from a faint, distant smudge of light isn't as direct as pointing a ruler at it. It relies on measuring how the light's colors are distributed and comparing that distribution to models of how stars of different ages and types should shine. If those models are subtly miscalibrated for this incredibly early, poorly understood era, especially assumptions about how efficiently gas turns into stars, or whether these earliest stars behave differently than the stars nearby galaxies are built from, then a mass estimate could come out artificially inflated. Under this explanation, the galaxies are real and early, but not quite as impossibly massive as the first calculations suggested, and once modeling techniques catch up to this new frontier, the numbers should settle down into something less shocking, though still remarkably early. That explanation would be reassuring, and it may account for at least part of the puzzle. But follow-up observations, using different instruments to independently confirm distances and refine mass estimates for several of the most extreme candidates, have not made the problem disappear. Some individual candidates have indeed been revised downward once additional data came in, exactly as the cautious explanation would predict. But others have held firm or even been confirmed as genuinely more distant, meaning genuinely earlier than first thought, deepening rather than resolving the tension. Which brings the debate to the second, far less comfortable possibility. What if the measurements are basically correct, and the actual problem is with the model of how galaxies form? If some of these massive, structured galaxies really did assemble within the universe's first few 100 million years, the standard, patient, merger-by-merger model of galaxy growth may be missing something significant about how quickly matter can collapse and ignite into stars under the right early conditions. Perhaps gas in the extremely young universe converted into stars far more efficiently than current models assume, building mass faster per generation of star formation than anyone expected. Perhaps the dark matter scaffolding that ordinary matter falls into and collapses along behaves slightly differently in some early regimes than current simulations capture, allowing structure to clump and organize faster than the standard timeline allows. Perhaps there is an entirely new physical process at work in this earliest era, one that has no clear analogue in the later, better studied universe we're used to observing, quietly accelerating the entire construction timeline in a way nobody anticipated. Any of these would represent a genuine gap in a framework that, until now, had done a remarkably good job of matching almost everything else astronomers observed about how galaxies grow and evolve. That's what makes this puzzle different from a simple case of we found something surprising. It isn't one anomalous object sitting alone in an otherwise tidy dataset. It's a pattern, showing up across multiple independent candidates, found by multiple research teams, using multiple analysis techniques, all pointing in the same uncomfortable direction: structures that are too big, too organized, and too early. Consider what's genuinely at stake if the extreme end of these findings holds up under continued scrutiny. Almost every model describing cosmic history treats the early universe as a slow, patient construction site, a place where nothing complicated exists yet because there simply hasn't been enough time. If genuinely massive, structured galaxies existed within the universe's first few 100 million years, that foundational assumption doesn't just need a minor adjustment. It needs a fundamental rethink of how quickly the earliest stages of the universe were capable of building complexity, a timeline compressed dramatically tighter than the standard model currently allows. That rethink wouldn't stay contained to just this one puzzle either. The same physics used to predict how quickly early galaxies should form feeds into calculations about how quickly the first stars ignited, how early the universe's fog of neutral gas was cleared away by that starlight, and how the largest structures in the universe, the clusters and filaments spanning unimaginable distances, eventually took shape. Pull hard enough on the galaxy formation timeline, and threads connecting to nearly every other chapter in cosmic history start to tighten as well. Right now, more observing time is being dedicated specifically to nailing down distances and masses for the most extreme of these early candidates, because resolving this question sits near the very top of the priority list for modern cosmology. Some of the most eye-catching initial claims have already been walked back slightly as better data arrived, a healthy and expected part of how frontier science operates. But the core surprise, structures existing earlier and larger than the standard model predicts, has not been explained away entirely, and every observing run adds new candidates to the pile rather than quietly resolving the old ones. Which leaves this page of the story in a strange, almost paradoxical state, describing galaxies that, according to the timeline every other page in this book has carefully built up, should not have had enough time to exist yet. And yet there they are, caught in light that has been traveling toward us for over 13 billion years, patiently waiting for someone to notice the timeline doesn't add up. 4 pages now, each one torn, glued shut, or written in a script that doesn't quite match the rest of the book. A universe pointing in a direction it shouldn't have. A cold patch that may remember a universe before ours. 2 clocks measuring the same expansion at 2 different speeds. And now, structures too massive, too organized, and too early to have been built by the rules we thought applied. 1 page remains. And it asks a question just as unsettling as all 4 combined. What do you do when you find something in the universe that appears, by every calculation, to simply be too big to exist at all? 4 pages torn, glued shut, or written in a script the rest of the book doesn't recognize. A direction the universe shouldn't have. A cold patch that might remember something else touching ours. 2 clocks disagreeing about how fast everything is growing. Galaxies too big, too soon. And now, the final page, the one that doesn't just challenge a measurement or a timeline, but challenges the very idea that the universe is allowed to have a size limit on how big anything inside it can be. Every model of the cosmos rests on a single foundational assumption. one so basic it barely gets mentioned once you get past the introductory chapters. If you zoom out far enough, the universe should look roughly the same everywhere. Not identical in every detail, but statistically uniform, with no region dramatically denser, emptier, or more structured than any other, once your scale is large enough. This idea has a name, the cosmological principle, and it isn't just a tidy philosophical preference. It is the load-bearing wall underneath nearly every equation used to describe how the universe expands, ages, and evolves. Without it, you cannot simplify a universe of unimaginable complexity into equations simple enough to actually solve. That assumption comes with a built-in prediction. There should be a maximum size beyond which no single structure, no wall of galaxies, no chain of matter should reasonably exist. Calculations based on how much time has passed since the beginning, combined with how fast structures can plausibly grow under gravity, put a rough ceiling on this, a scale beyond which any single connected structure would represent enough clustering to make the smooth, evenly spread universe. Astronomers went looking for structure at the largest scales anyway, mapping the positions of galaxies across enormous volumes of space to see how matter clumps together into filaments, clusters, and the vast empty voids between them. What they found, again and again, are structures that sit uncomfortably close to that theoretical ceiling, and in some cases appear to blow straight through it. Consider a sprawling arrangement of galaxy clusters discovered stretching across an almost incomprehensible span of space, connected together into a single, loosely bound structure so large that light would take billions of years just to cross from one end to the other. Structures like this are given names that sound almost mundane, walls, given how extraordinary they actually are, but the numbers involved are anything but ordinary. A structure spanning a significant fraction of the entire observable universe's width isn't just large. It sits at, or arguably beyond, the size where the standard model insists nothing should have had enough time to clump together into one connected arrangement. That alone might be dismissed as a single outlier. An unusually generous connecting the dots exercise linking together clusters that only loosely belong to one continuous structure. But it isn't alone. Separately, astronomers have identified groupings of ancient, extremely luminous objects, the blazing centers of distant galaxies, where supermassive black holes are actively feeding, clustered together across similarly vast distances, forming their own enormous, loosely bound arrangements. And separately still, giant elongated arcs of galaxies have been mapped, curving across the sky in configurations that, if real and physically associated, rather than a coincidental alignment along our line of sight, would represent some of the largest coherent structures ever identified, again pushing up against or past the size where current models say clumping this extensive shouldn't yet be possible. Each of these discoveries, considered individually, invites the same first, most cautious question. Is this actually one connected structure, or is it an optical illusion created by loosely related objects that happen to sit along a similar line of sight, appearing connected only because of how we're viewing them from one particular vantage point? This is a serious and reasonable objection, because determining whether galaxies separated by such enormous distances are truly gravitationally bound into one system, rather than merely appearing grouped from our specific viewing angle, is genuinely difficult. Distance measurements carry uncertainty. Grouping algorithms make judgment calls about how close is close enough to count as connected. A structure that looks like one continuous wall from Earth's vantage point, could, in principle, be several unrelated clusters that simply happen to line up. That objection has real weight, and it has narrowed some of the more extreme initial claims. Careful follow-up analysis on a few of these massive structures has shown that some portions are less tightly connected than the original discovery papers suggested, chains that looked continuous turning out to have gaps, or looser physical association than first claimed. Science working exactly as it should, tightening an extraordinary claim down to something more defensible. But that scrutiny has not made every one of these structures disappear. Some have survived repeated independent remeasurement, using different galaxy surveys and different statistical techniques to test whether the clustering is real or an illusion of perspective, and continue to hold up as genuinely large, genuinely coherent arrangements of matter. Still sitting at or beyond the size where the standard cosmological framework says clustering this extensive shouldn't have had time to form. And that is precisely where this final page stops being a curiosity and starts being a direct challenge to the rulebook itself. If the universe isn't supposed to have a favorite side, isn't supposed to build single structures larger than a specific theoretical ceiling, and yet it clearly, repeatedly does, in multiple independent surveys, using multiple different types of objects, found by multiple separate research teams, what does that say about the rulebook we've been using? The stakes here reach even further than they might first appear. Because the cosmological principle isn't just one assumption sitting quietly in a single chapter, it's the load-bearing foundation underneath essentially every other calculation in this entire story. The expansion rate, the age of the universe, the interpretation of that ancient afterglow of light, the models used to explain how galaxies assembled, all of it depends on treating the universe at sufficiently large scales as smooth and uniform. If genuinely enormous, coherent structures exist well beyond the size that assumption permits, it doesn't just mean one wall of galaxies is unusually large. It means the scale at which the universe is supposed to average out into smooth uniformity might be significantly larger than currently assumed, which would ripple backward into recalculating nearly everything built on top of that assumption, including, some researchers have speculated, potentially bearing on other unresolved puzzles already sitting on earlier pages of this very story. Nobody has proven that connection yet. It remains speculative, a thread some cosmologists are actively pulling on, rather than a settled conclusion. But the fact that researchers are seriously entertaining a link between the largest structures anyone has ever mapped and other stubborn anomalies elsewhere in cosmology tells you how seriously this final anomaly is being taken. As it stands today, several of the largest structures ever mapped in the observable universe continue to sit right at, or beyond, the boundary of what the standard cosmological framework says should exist. Some early, more extreme claims have been softened by careful reanalysis. Others have held firm despite that same scrutiny. And the deepest question underneath all of it, whether the universe truly averages out to smooth uniformity at some large enough scale, or whether that foundational assumption itself needs revisiting, remains unresolved. 5 pages now, each one refusing to close cleanly. A direction that shouldn't exist. A cold patch that might remember another universe. 2 clocks that can't agree on the present. Galaxies built faster than the rules allow. And structures wider than the universe is supposed to permit. Reading this book all the way through doesn't leave you with a tidy final chapter. It leaves you holding the same object you started with, filled with more torn edges and unfinished sentences than you realized when you first opened it, and the honest, current answer to every single one of them is the same. Nobody knows yet. Which, if you think about it, is the most interesting place any of us could possibly be standing. 5 pages, and not one of them closes the way a good story is supposed to close. No final chapter tying every thread together, no tidy resolution waiting on the last page to make sense of everything that came before it. Just 5 separate, stubborn anomalies, each one surviving every attempt to explain it away, each one still sitting there, unresolved, the last time anyone checked. Think back to where this started. A book, except several of its pages are stuck together, refusing to separate no matter how carefully you try to peel them apart. A few have been torn out entirely, leaving jagged, unfinished edges, where the story clearly continues. Somewhere, just not anywhere we can currently read. And a few pages seem to be written in a language none of us have fully learned yet, familiar enough to recognize as language, unfamiliar enough that translating it completely keeps slipping out of reach. A universe that appears to remember a direction it should never have had, still unexplained. A cold, oversized patch of ancient light that might be the faint, contested fingerprint of contact with something outside our own universe, still neither confirmed nor ruled out. 2 independent, careful, aggressively double-checked measurements of how fast everything is expanding right now, refusing to agree with each other no matter how much data gets thrown at the problem. Galaxies discovered fully formed and startlingly massive at a point in cosmic history when, by every existing model, they should still have been disorganized infants, and structures so vast they brush up against, or exceed, the very ceiling the universe is supposed to enforce on how large anything is allowed to grow. None of these are settled. None of these are safely tucked away in a textbook with a confident, final answer attached. They are live, contested, actively argued over pages, sitting in the hands of researchers right now, in real time, while you've been reading this. And maybe that's the part worth sitting with longer than any single mystery on its own. It would be one thing if these were 5 unrelated curiosities, scattered oddities with nothing in common beyond being strange. But look at what they actually share. Each one starts as a small, almost forgettable discrepancy. A number slightly off, a patch slightly too cold, a structure slightly too large, easy to dismiss on its own as noise, an error bar, a fluke, and each one, instead of fading as better instruments and more careful analysis arrived, got sharper, more statistically serious, harder to explain away. That pattern, small anomalies hardening rather than dissolving under scrutiny, is usually how real discoveries begin, long before anyone is confident enough to call them by that name. Maybe every one of these pages eventually gets read in full. Maybe a decade from now, each mystery collapses into some elegant, satisfying explanation, folded neatly back into a slightly revised version of the same framework we already trust. And future viewers look back at this exact list the way we now look back at solved puzzles from 100 years ago. Quaint reminders of how much even brilliant people didn't yet understand. Or maybe one of these pages, maybe more than one, turns out to be the beginning of something far bigger. A genuine crack in a foundation that has otherwise held remarkably well for a very long time. The first hint of an entirely new chapter nobody has written yet, because nobody currently has the vocabulary for it. Nobody alive today knows which outcome is coming. Not with certainty. Not yet. What we do know is this: the same sky you can walk outside and look up at tonight, ordinary, familiar, endlessly repeated across a lifetime of glances, is quietly holding pages we haven't finished reading. Somewhere in that light is a direction that shouldn't exist. A bruise that might not be ours alone, a clock running at two different speeds, a birth that happened too fast, and a wall too wide for the rules we live by. So the next time you look up, ask yourself honestly, how many more pages are still glued shut, torn out, or written in a language we simply haven't learned to read yet? Right there, above your head, waiting.